In this notebook, we actually do two things, but I'm only going to cover one today, is the estimation of the SLX model. And as of this summer, there's also nonlinear SLX, but today I'm just going to cover linear SLX models. And what is different from what we did the other day, where when we looked at the Lagrange multiplier tests, we ran the model with OLS and then also ran an SLX, because you can run SLX with OLS. The spatially lagged explanatory variables are just exogenous variables like anything else. For practice, that makes it really attractive. From a theoretical point of view, this makes it uninteresting because there's nothing special. From my perspective, there is something special, and that is, what do you put in the weights? Because now the weights become very important in that you don't have this automatic reduced form, which gives you Tobler's law distance decay very nicely. Now you let the parameters be whatever they are. Do they necessarily make sense? Well, from my perspective, sometimes not. And what do you do then? From my perspective, you drop them. Okay. And also, since this summer, you can do that in SPReg. So there's an option called SLX vars, which lets you drop, actually lets you specify which WXs you want to keep. And so now we have a lot of flexibility. We can use different spatial weights. We can keep some of them in the spatial lag and others not. And in addition to the standard row standardized weights that we've been using so far, we can now also use kernel weights. Kernel weights are nonlinear. The row standardized weights are, in a sense, linear because the weights are all the same. In a kernel weight, the weights are a function of distance away. And so that's one kind of cheap way to put in some nonlinearity. Then the fancy way is to make the weights actually functions, nonlinear functions of distance. And that's the nonlinear SLX. I'm not going to talk about it much today because it's tricky. It's very tempting because it seems like it's more sophisticated than the linear weights. In my experience running this, very often you get parameter values that, when you look at them closely, actually imply that there is no spillover effect. Because inverse distance weights and exponential weights, as we've seen before, they go down very quickly. If your parameter is larger than 2, for example, it goes down very steeply, which essentially zeroes out any observations that are further away than even half of the bandwidth, or sometimes even a quarter of the bandwidth, which means for all practical purposes, there's no spillover, right? So we're not going to go there. We use all the same modules as before. This imports NSLX, but we don't actually need that today. So if you import everything, we should be good to go. The setup is always the same. We use the same data set, sample data set. We use this, I do this on purpose. We use a specification for which the lag model actually makes sense. If you recall, when we did our specification tests for the immigrant paradox model, there wasn't a strong evidence for a lag model. So this one, there is. It uses the hardship index, this one, as the dependent variable. Remember, it used to be an X variable. And then same ethnic variables and the percentage without a high school diploma, basically. And then to compute the kernel weights, we need X and Y coordinates. If that seems strange to you, go back to the notes on spatial weights and how you can make kernel weights in PySAL. Here we specify everything. We specify the file name. We specify the dependent variable, the explanatory variables, the names for the weights in the data set, the coordinates, and the ID variable. These are all kind of details that we need to make this work. And then in the third step, we actually set it up. We read the file. We get the queen weights for contiguity. These are the standard row standardized weights. And then we create two kinds of kernel weights using weights kernel function. We pass the coordinates as an array, 10 variable bandwidth, 10 k nearest neighbors, fixed as false, and we have the diagonal. The first one uses the default function, which is triangular. The second one uses a quadratic kernel weight. Okay. So here we go. There's a lot of explanation. We can go straight to the OLS case. So point of departure is just because we have never estimated this model before. We estimate the SLX, the OLS, and we check the spatial diagnostics, right? And of course, you know, I cheated. It's a very nice model. Everything is significant. Good fit, more than 80%. And if we look at our diagnostics down here, lag, significant, robust lag, significant, error significant, robust error significant, but the lag is more significant than the error. So there's strong evidence here for a lag model. The robust tests are nicely smaller than the original ones. Everything's good. If we go to the spatial Durbin model, which is actually also a lag model, but a lag model with extra SLX terms, we have strong significance of WX, also robust. The robust, this case, is smaller than the original. Remember, we had some issues with that when we looked at the diagnostics tests. And the lag is also highly significant. So there's evidence for lag, there's evidence for spatial Durbin, right? First, SLX estimation uses OLS. This is OLS, Y and X, the weights. And the only difference is this option. This sets SLX lags equal 1. The default setup is that it's 0. So there's no spatially lagged explanatory variables. Everything else is as before. So there's nothing new here. We can do robust errors, everything. All that stuff is the same as before. And now we have the output, or ordinary squares with spatially lagged X. Everything looks the same because it is the same. It's an OLS estimation. And now we see here that the list of variables, you don't have to do anything, right? You don't have to add them to the X's. It's all done under the hood. Okay. Given the weights, we know what the spatial lags are, we stick them in. Okay. We don't compute a spatial lag for the constant term. So all this is taken care of under the hood. We have the coefficients here, and they're all significant, but remember my pet peeve. Don't just take this at face value. We have the effect of black percentage in the census tract is positive, black percentage in the neighboring census tract is negative. You give me a good explanation for that, and I'll take it. I can't come up with one. Okay. Same for Hispanic, opposite signs. If you have a good explanation, fine. If not, then this doesn't make sense. In the following meaning, that we are forcing a specification on the data that is not supported by the data. Remember, we make up these models. There's nothing that says that this is the proper model to use. So we can force whatever model we want. If the data say, no, sorry, this doesn't work, it will give you weird results. Sometimes these weird results are poor fit. You know, you have an R-square of 0.1, you say, okay, no way. This is mostly noise, there's nothing here. Sometimes it's in the form of coefficient estimates that don't make any sense. Sometimes in economics, your coefficient has to be less than 1. If you get a coefficient that's larger than 1, that means you're forcing a model on the data that the data don't support, right? A lot of times in production functions, those kinds of things, you can get estimates that don't make any sense in a substantive way, but the estimation gives them to you. This last one is good, but it's larger than the coefficient for the census tract itself. So the percentage without high school diploma in the neighboring census tracts is more important than the percentage without high school diploma in the tract itself, which violates, for what it's worth, Tobler's law. Waldo was a colleague and a friend of mine. I don't want to violate his law. Okay. So when I see this, I say, let's wait a minute. Okay. We go to the diagnostics, and what do we see? Both original error, lag, and error are significant, but the robust ones are not. The rule of thumb is that we go with the most significant one, which would suggest a remaining error specification. Now, we can deal with that because we can do a hack. Or we can deal with that later when we know how to estimate the error modes. But that's not till next week, right? If we can put in first order lag, we can put in higher order lags just by setting SLX to a higher value. But as I mentioned, that is often not such a good idea. And I'll show you why, because I will show you probably the highest VIFs that you've ever seen. If you've ever looked at VIFs, variance inflation factors. Remember, the variance inflation factor has to do with how well a variable, an X, is explained by the other X's. The higher the fit, the worse the VIF. Right? So we run this, and we have, again, built in these second order weights. None of them is significant. So in other words, it was a waste of time. We shouldn't have done this. But the interesting part is down here. You see these more than 100? What that means is that the R square, and we did this when we looked at OLS, the R square of the regression of this variable, so this one, W2 of the black percentage, is higher than 0.99. For 0.99, the VIF is 100. For 0.95, the VIF is 20. So you see that this creates, and you can see it here too, the multicollinearity diagnostic number is almost 90, which is well above the rule of thumb of 30. Now, there's nothing magic about that rule of thumb, but once you get big numbers like this, you have to start being a little nervous about it, okay? So there's no point. There's nothing gained by introducing these higher lags. Another strategy we can follow is kicking out some of these spatial lags by selectively keeping some. And as we saw in the results, from my perspective, the only one that made somewhat sense was the neighboring no high school diploma. The other ones were negative. And you can do this by specifying SLX vars. The default for SLX vars, and that's why you don't see it when you run it, is all. So all the X variables get a spatial lag in the specification. If you specify a list with Booleans, then it picks out only the one that is true. Now you have to make sure that the sequence is the correct sequence, otherwise you're in trouble. So this isn't foolproof, right? If you mix up the order, you're in trouble, but you'll see it right away in the listing of results. In our example, we only keep the last one, so it's false, false, true. And if I run this, you see now, I'm not going to pay attention to the other things. We have all significant. Now the Hispanic percentage becomes non-significant. But most importantly, for Waldo Tobler, the coefficient of the neighbors is smaller than the coefficient in the unit itself. Okay. That's distance decay. If you don't have distance decay, you have something weird. If you have a good explanation for that something weird, I'm good with that, right? I'm not going to insist on distance decay, but distance decay makes sense. This other stuff may not make sense. Okay. Keep this in mind when you do your empirical exercise. So since the summer, we can also do SLX models with kernel weights. You can't use kernel weights for spatial diagnostics. You have to use row standardized weights, the classic type that we saw. But if you specify the weights here, W is WK10, which is our triangular kernel weights that we just constructed, then that is used to make the spatially lagged X variables. As I mentioned, that is an explicit form of distance decay because you built it in the distance decay of the kernel function. The triangular kernel function is a triangular decay that goes to 0 at the bandwidth. So if we run this, it looks as before. We still have the negatives. Everything is significant. The interpretation of the coefficient is a little more difficult. In fact, to truly know what the impacts are, you have to run this impact simulation, which we didn't cover, but it's in one of the notebooks. One of the notebooks is called Spatial Impacts. That gives you the types of maps that we saw in class when we looked at the multipliers, the effect on the neighbors, the effect of the neighbors, individual specific, we could map them. So you could do this with these coefficients, just like with any other model. We can run it again with the one variable left, and again, everything is fine, and same as before, the Hispanic percentage becomes non-significant. In terms of fit, they're all pretty much the same. There is actually, you can look at the sum of squared residuals. That's something that you can compare between the different models. And there isn't anything gained by using the kernel in this particular example. Sometimes there is. And then finally, we can use a quadratic kernel. This is the one here. So in all other respects, this is the same as before. SLX lags equal 1. I now put it in here explicitly, but you don't have to because it's the default. So everything looks the same as before. We have the 3 spatially lagged variables with their coefficients. And then here we have SLX vars false, false, true, to just pick out the last one. And again, we have the similar result, qualitatively similar result. So at the end of the day, it does seem to make sense to include one spatially lagged explanatory variable. Using the kernel weights doesn't really buy you anything in terms of better insights or greater fit or anything like that. That's just in this example. That's by no means a general result. So nonlinear SLX will be covered in the topics course.